Good afternoon. I'm Helmut Hofer. I'm a faculty member in the School of Mathematics. So welcome, everybody. I want particularly to welcome Maria and Visi Morse, who are following this event online. Morse theory can be regarded as one of the great mathematical achievements of the 20th century. It started with a paper by Marston Morse, which appeared precisely 100 years ago. It was called Relations Between the Critical Points of a Real Function of n independent variables. So that might not tell you too much, but it is a type of problem which today, the things have further developed, actually address many, many problems which are of interest, for example, geometry, topology, and physics. So the development since then has been breathtaking. And to celebrate this occasion appropriately, we are honored to have today with us Étienne Ghys, one of the leading mathematicians celebrated for his exceptional work in geometry and dynamical systems. And on top of it, Étienne is also known for his engaging approach to sharing mathematics with the broader audience, which I think is something extremely important. So today he will guide us through fascinating mathematical ideas, and the title of his talk is Slicing Spaces from Contour Lines to Morse Theory. Étienne, the floor is yours.
Can you hear me? Yes, good. Okay, so let me show you first this. You see this giraffe? In France, it's very famous giraffe. It's a typical gift for newborn babies. And I was in France not long ago in an artistic exhibition, and I saw the giraffe sliced into pieces like that. And I said to myself, well, this is Morse theory. And on the right, this is a picture that you must know because I took it a few moments ago in the other building next to this place. Okay, let me begin by showing you the most famous Morse. This is Samuel Morse, the creator of the Morse code, known everywhere in the world a little bit more than our Morse. So as Helmut said, we are here to celebrate the 100th anniversary of one paper. I love celebrating 100th birthday. I already did that several times. The birthday of fundamental group, 1891, with a beautiful cake, non-simply connected. I celebrated the birthday of the Lebesgue measure, 1901. I celebrated the birthday of the uniformization theorem, 1907. I think it's a good opportunity to have a look at backwards and try to understand how things happened. So we have to discuss not only this paper, but its origin. Where does it come from? Why things arise this way? But before that, I want to show you how popular and famous Morse theory is today. Here's a graphic. This is the number of quotations in mathematical papers containing Morse. You see that today it's about 3 papers per day mentioning Morse. You might say this is should be compared with the total production of mathematics. So here's the similar curve for the total number of mathematical publications since 100 years ago by decades. I think this curve is frightening. This is a shame. Too many publications. I mean, we should stop publishing so many papers. We are losing unity of mathematics is fundamental. If we are not able to read what's happening in mathematics, we are lost. So please stop writing papers. Please stop writing bad papers. So in order to see if Morse is still popular today, of course, I want to measure not only the number of papers, but the proportion of papers relative to the total production of mathematics. Here's the result. It's good. It's very good. You can see that today, mathematical papers mentioning Morse is about 1%. This is fantastic. I mean, so you told me that the daughter of Morse is here too. Congratulations for your father. You just imagine 1% of the papers contain the name of your father. This is something fantastic. Okay, so I want to discuss not only this paper of Morse, but I want to discuss the prehistory. And first of all, I want to discuss the history of contour lines. We are used to look at maps with contour lines, like, for example, this one in the neighborhood of this place. You know, these red curves where the altitude, the elevation is constant. This is not completely obvious. Who had the idea of drawing this kind of picture? And it turns out that the first picture like that is not for elevation, but it's for depth. So here's the very first picture of contour curves, 1730. They are drawing pictures of the contour lines in a river in the Netherlands. This is fundamental for your boat. This is much more fundamental that if you are hiking, it's not so important. Well, it's important to know if you're going up or down, but nevertheless, it's more important for the boats. So here's the picture. Let me have a look more precisely. You see the drawings of the contour lines. If you look carefully, you can see that this kind of picture here is suspicious. It does not look like an actual system of contour lines. There's a mistake somewhere. We will see that later. Anyway, this is not mathematics. It's just picture useful for boats. And you had to wait a long time before it became mathematical. And here's the first mathematicians who understood and described the structure of contour lines. He wrote a wonderful paper in 1859 on contour and slope lines. And this is just a jewel. This is fantastic. He says, let's have a look at the global picture of contour lines in a standard map. And he makes a lot of observations. I will mention some of them now. He makes a lot of observations. Some of them are really incredibly modern. First of all, he says, well, okay, we slice like a giraffe. Huh? You slice the mountain by horizontal plane, and we want to understand the nature of these contour lines. And then he says, okay, there are several specific points, summit, this I understand. Then it creates, I don't know if, is it an English word? Emit. Do you know this? Does that exist? Yes, it does exist. Emit is the opposite of summit. When I looked in the dictionary, I did not find it. It does not exist. Okay, it's a creation of Cayley. He created the word emit as the opposite of summit. How would you call that in English today? The bottom? What? A base. Is there any proposal? Minimum is too mathematical. I mean, how would you say it when you hike? Anyway, emit is good. And more incredible, for what we call saddle, he calls that a knot for some strange reason. And then after describing these three specific points, he discusses the structure of these contour lines. Very explicitly, he says that if you have a point which is neither a summit nor emit nor a knot, locally, what you see on the is like on the left-hand side, you have beautiful curves parallel to each other. In the neighborhood of a summit, you have a concentrical circle, and in the neighborhood of a knot, you have something like that. What is interesting is that he is very aware of the fact that this picture is not the general case. He knows exactly that this is a generic situation. And he says that with great precision. He says, okay, it's not always like that, but in general, you can expect that the lines should be like that. And then he makes a comment about the contour lines going through these knots. And he says, well, it could be like that, but this is too specific. Usually this does not exist. And he says the following: although there may be neighboring passes of precisely the same elevation, yet the general configuration of the country will not be altered by giving a slight difference of elevation to such passes. In other words, I think it's one of the first examples in mathematics where you describe a generic situation. In general, you should expect that from a map. And then he looks at the situation very explicitly. What is the contour line going through a knot? And he said, well, there are two possibilities. It could be like that, like an 8, or like the second picture. The first one, he calls that an in loop, an out loop. And the second picture, he calls that an in loop. This is really a fascinating paper. No theorem, just explanation. Don't forget that in 1859, topology did not exist. He's just describing pictures. And here's an example of an in loop. If you slice it, you get that. Okay? And this is explicitly explained by Cayley. You know, when we speak of Cayley, usually we think of an algebraic mathematician, but this is very topological. Okay, this is again a wonderful paper. But he then goes to understanding the slope lines, the line of gradients. If you are in a mountain and you go to the steepest descents, what do you get? And you get this picture, the blue lines, going from a summit or going from a knot or a saddle, and you have this local picture. So he explains that with great details. And then he says, look, there is specific lines going from one summit to another one through a saddle, and these specific lines are called, he calls that ridge lines. In French, we say ligne de crête. And what's amazing is that the paper of Cayley is full of French. He says, as the French would say, ligne de fête. Anyway, so this is very interesting. You understand what is the we call that saddle connection today. So this is very important. This line goes down to the saddle and up to the next summit. And then that's not enough. You want to understand globally the picture, and you have something like that. Oh, here's a more global picture. You have here summit, a saddle, another summit, a saddle, up. Oops. You have here a summit, saddle, summit, and these lines determine what is called the watershed. This is a locus of points where a drop of rain will go to the same point. And then, perpendicular, so to speak, you have the blue lines going away from the saddle, going down and down. And then he calls that the German word Talweg lines. These are typically the lines of the rivers. The water comes from the saddle goes down to the valley, and typically a river will be created along these lines. So this is the paper of Cayley. Basically no theorem, just no picture, just text explaining the picture. And to have a picture, you have to wait a little bit more by some other mathematician very well known, Maxwell. Maxwell wrote this paper called On Hills and Dales. So I don't know what Dales means, but this is the same topic. In the introduction, he says, my paper is not original. My paper is the same as the paper of Cayley. However, he draws pictures. And one of the pictures is this. You know, you have this beautiful global picture with summits, saddles, etc., etc. He wants to understand the global topology. So this is just description, no theorem. And somehow it's useless. I mean, it's just to understand maps. The first one who used this kind of ideas, not for description, but for proving theorems, is Möbius. Möbius, I think, is the first mathematician who kind of proved a classification of surfaces in a very, not completely rigorous, but very interesting situation. Let me show you what he did. He wanted to, here's this paper. It's not easy to read, first of all, because it's in German, but second of all, because, of course, there was no tools from topology at the time, so he had to translate everything. So, for example, at the beginning, he says, two geometric figures shall be called elementary related to one another, or today we would say two manifolds are homeomorphic if. So he's trying to understand the relation between surfaces or manifolds in general, classifying them up to homeomorphism. And so he says, how can we do the classification of surfaces? Of course, his surfaces are not our surfaces, are not abstract. They are embedded in 3 space. And he wants to understand them up to continuous bijection. And what he does, he says, well, we are going to study maps. We are going to study what we call today Morse functions and try to understand this structure. So he started this way. You have the surface, you slice it by horizontal planes, and you try to understand how the situation changes when you go from one level to another level. It's always 2-dimensional. And then he draws pictures and he writes formulas. Look at that. For each slice, he writes a letter. For example, you see A, B, C, D, and then he observes that in between 2 slices, you have a small number of topological configurations. It could be a pair of pants, like on the right. It could be a cylinder, like in the middle, or it could be just a disk like on the left. He knows that very well. He doesn't prove it, of course, but he knows that. And then he says, well, when I go from the top to the bottom, I will be gluing cylinders, pairs of pans together, and finally I get the surface. And then he does the following. He introduces some combinatorics in the following way. Look at on the left, you have A, B, C, D, E, F, G, H, I, until Q. If a letter is followed by a cylinder, you put in parentheses these two letters. For example, you see here, BD. BD, B is here, D is here, B and D are connected by a cylinder. If you look at ABC, you see ABC together create a pair of pans. So if you have a pair of pans, you took a triple parenthesis. And so you see, for example, here, DGH is a triple parenthesis. So he does that. And then he begins with a kind of complicated, very complicated combinatorics to see when you can modify these parentheses to create a new surface which is homeomorphic, but with a different Morse function, so to speak. And he does a combinatorical description, and at the end of this paper, he has a theorem. The theorem is that any surface is homeomorphic to one of these. This is a fundamental theorem today in mathematics, and this is, I think, the first time in history where somebody proved it. Of course, the proof is not convincing. In many places, you say, hey, you forgot that, or you forgot that. But anyway, the structure of the proof is wonderful. It's using a Morse function and reducing it to some combinatorial question, which is basically what we do today, basically. So this paper of Möbius is really a fantastic paper, which uses contour lines to prove something in mathematics. The next is the best, Poincaré. Poincaré, it's really amazing because Poincaré, of course, he knew everything in Morse theory, or everything, maybe not everything, but a lot of things. He never mentioned it, but he uses a lot these ideas of looking at the level sets and how they evaluate from one level to the other one. And he has motivations. The motivations of Poincaré are very clear and very explicit. He wants to study topology, as he called it, analysis situs, with several motivations. One was dynamical systems. The other one was algebraic geometry. And the third one was, in a strange way, number theory. He wanted to understand discrete subgroups in linear groups. Very explicitly, this is his first paper, has 3 parts, and this is the 3 motivations. And today I will only mention one of his motivations. It is the idea of using topology or analysis situs to understand dynamics, and typically to understand celestial mechanics, and typically to understand the 3-body problem. So here's a picture. Now here's one of the papers that he wrote. This is one of my favorite papers of Poincaré. He wants to study a convex body in 3 space. And his goal is to prove that on this convex set, you can always find a closed curve, which is a geodesic. He gives 3 proofs of this fact. None of them is correct, but all are very interesting. And all had the descendants in the future. And he explicitly mentions that finding a geodesic on a convex surface is by itself not so interesting. But he gives a motivation for that coming from dynamics. Look, he says, oh, this is in French. In my, he says that I forgot to translate it in English. He says, look, geodesics is the easiest problem which is close enough to mechanics and that you can understand. Finding geodesics is the way to understand dynamics. And this is his only motivation. I think he doesn't care about geodesic on surfaces. He cares about the motion of planets. And then let me give you one example to understand that. This is the so-called Hill's potential. You have the sun, let's say the moon rotating around the sun. You may assume for simplicity that the moon is rotating on a circle in a plane, and you change coordinate in such a way that the sun is fixed and the moon is fixed. And then you imagine a body, a very small body, which is attracted both by the sun and the moon. And you want to understand the dynamics. And what Poincaré says is that it's not difficult to use what's called the Hill's potential to express this motion of this small body as the motion of a geodesic on a sphere. And finding a closed trajectory for closed geodesic is just the same thing as finding periodic orbits for the three-body problem. This is a wonderful paper. He wrote many papers on celestial mechanics, including several books, which are just landmarks in the history of celestial mechanics. But this is one example. And there, his proof is very much concerned with Morse theory, even though he does not use, of course, the word, but not even use he uses the ideas without mentioning them. It's not always easy to read Poincaré because it's always brilliant and frequently wrong. Okay, so who were the heirs of Poincaré? Obviously, two mathematicians, both with strong links with Princeton, Lefschetz and Birkhoff. Lefschetz was in charge of algebraic geometry. He was, his duty, his idea was to use analysis situs, topology, in order to understand better algebraic geometry. And we all know that he did this with great success. And Birkhoff was, I think he was a member here, no? No? I think so. Anyway, Birkhoff was more interested by the dynamical systems and the use of topology in dynamical systems. So I will not go to Lefschetz. Let me go to Birkhoff, because of course Birkhoff was the advisor of Morse. And now let me go to Morse. Morse did a great transformation in this theory. Let me tell you, this is paper 25. And then it's clear from this paper that he is directly concerned with dynamical systems. His motivation is dynamical systems. And, oh, this is Birkhoff. And one of the main ideas from Birkhoff was to get a proof of the existence of a periodic geodesic on a convex surface. But this kind of proof is now correct. I think this is the first proof which is correct. And his idea was to use the so-called minimax principle, which is basically the following. You have a sphere, a convex body, and you want to find on it a periodic curve, which is a geodesic. So one idea would be to take the shortest one. But the shortest one is not good because the shortest one actually is a point restricted to one of the poles. So what you do is that instead of looking for one curve, you look for one parameter family of curves coming from one point to another point, and you try to find this family of curves in such a way that the maximum of its length is the minimum possible. It's a minimax question. And if you do that, you arrive at a geodesic. The proof is wonderful. I think it's today is one of the fundamental ideas in geometry, the minimax principle. Okay, at last, Morse. What is the main contribution in Morse in 1925? Several points. First, he goes from dimension 2 to dimension n, which is quite a lot. And even more, he went from dimension n to infinite dimension, even better. And then his starting point is the following. You start with a function, like a height function on a manifold. At this time, manifold was kind of clear. You look at critical points where the differential is 0, and then he expresses the non-degeneracy of critical point. This is a point where the Hessian second derivatives is non-degenerate, and he calls the index the number of negative eigenvalues. And finally, a Morse function today is called a function such that all critical points are non-degenerate. This is the standard, the setup of Morse. And what he does is the following. First of all, the famous Morse lemma, which appears in his paper in kind of hidden way, but it's there. He says that if you have a critical point which is non-degenerate, in the neighborhood of this critical point, in suitable coordinate, you can assume that this is really a sum of squares, sometimes with plus and minus signs. And then this is the so-called Morse lemma. And then you can look at the sublevel, well, where the function is less than some a. And then you have two basic theorems. One is that if in between two values, a and b, if you compare the sublevel a and sublevel b, you have something like the cylinder that we had before. You have just a product, nothing happened. And if you have one critical point, this is the main theorem, you go from the sublevel A to the sublevel B by gluing a cell whose dimension is the index of the singular point by some gluing map. So this is today, I mean, today is somehow easy for us, but the proof given by Morse is not so easy to read. But anyway, everything is there. And then using that, he proves the Morse inequality. If you have a Morse function, you can count two numbers. The first number is the number of critical points of index k, and the second is the number, the Betti number, the dimension of the kth homology group. And then the theorem is that ck is greater than or equal to bk. So that means the following. The topology might force critical points. If bk is not 0, then ck is not 0. So if you know something about the topology of a manifold, like for example, some Betti number is not 0, you know that there has to be a lot of critical points. That's the main idea of this paper, and he uses it in using infinite dimensional manifold, loop space of curves. You can space of curves from a point P to a point Q, and then this is infinite dimensional space, but you can somehow approximate it by some finite dimensional spaces, and then he gets the following, which is a wonderful theorem, that in between 2 points on any sphere of any dimension, endowed with any Riemannian metric, there are always an infinite number of geodesics connecting them. So this is an application, direct application of Morse theory, of topology to dynamics to geometry. This is, I think, a wonderful, very important theorem. And then the situation continued with René Thom. René Thom, he was very much interested by topography, by geography. I remember the first time I met him, he explained to me the plate tectonics. And he had a wonderful question. You know, plate tectonics, you have on the Earth some rigid plates. Each one is moving relative to the other. And now he asked the question, okay, if the sphere is covered by plates which rotates one with respect to the other, what is the definition of latitude? What does that mean, longitude? How can we find coordinate system on the Earth if everything is moving? And I remember his solution. I don't know if he published that somewhere. He says, well, when a plate is moving relative to another, so for each plate A and J, you have a motion xij, and this gives a cocycle. And since we are on the sphere, the cocycle is exact. And so that means that all these plates, after all, they are rotating relative to something that we can fixed. So he defined longitude and latitude. I remember that because you know, this great René Thom was interested by very concrete questions. And one of his, not one, his first paper in 1949, he is the following. Here you have a function on a space. I would say this paper is not due to him, it's due to Cayley. He says any function on a space decomposes the space in domains that we can call watershed. 2 points are in the same domain if gradient lines starting from these points go to the same point. And this decomposes the space into cells. That's the content of this paper, 1949. So let me show you an example. This is a map of France. And you can see the domain of the Seine, the domain of Garonne, the domain of each main river. And you have, in this way, a decomposition of the country in contractible domain, in cells, which tell you about the structure of the geography of the country. And this is exactly what Thom did. Now, let's go to Smale. Smale somehow began with the same idea. I don't really know if Smale was aware of Thom. Maybe yes, maybe not. There was no internet at the time. And he improved the idea of Thom by proving, or claiming at least, I don't know if he proved it, that if you take a Morse function on a manifold, it will decompose your manifold into watersheds, into domains of attraction. But he realized that if the function is generic, if the metric is generic, you can make sure that this decomposition of the space into domains is a good decomposition, in the sense that the boundaries are transversal. And that's very useful for him to construct something that I will show you now. You have here the picture in the case of a torus. And here it is, the decomposition in the North America. You might say there is something strange in this picture. This, no, this one. No, this one, the blue one. What is strange there? It's not going to the sea. Do you know your country? Do you know what this is? What? It's called the Great Basin. water, rain falling there does not go to the sea. It just goes in the earth or evaporate or something. So this is why this is the only place where it is not connected to the sea. Anyway, Thom, Smale, and later Witten improved this by constructing an algebraic gadget. And this is the Thom, Smale, Witten complex. You start with a Morse function, and you create a vector space over Z2, just one generator by each critical point, and you create a differential. The differential of X is the sum of all critical points Y of nxy y, where nxy is the number of lignes de fait, saddle connections going from X to Y. So Y is just one index lower. If you do that, you create a linear map, delta. It's not difficult to see that delta square is 0. So you can play the game of algebraic geometry. You can look at cycles, boundary, etc., etc. And the main theorem of Thom, Smale, and Witten is that this homology that you create is just a standard homology, singular homology that we all know today. And this is very simple to understand today. And this gives a very simple proof of the Morse inequalities. What is very strange that in 1959, somehow Smale did not use his main ideas so much. He wanted to generalize to some more complicated objects, which are dynamical systems. And he imagined, instead of having the gradient of a single function, he imagined a vector field in a manifold and tried to say what could be a Morse vector field. So if you think of a Morse function as being something where gradient lines go from one point to another point with very simple dynamics, he said to himself, maybe I should create the concept of Morse vector field having a finite number of periodic orbits, and the other orbits which are not periodic after some time will accumulate to this finite number of orbits. And we call that today Morse-Smale dynamical systems. And well, this is a good notion, except that the paper is somehow completely wrong in the sense that you have beautiful definition and not wrong. He conjectures something which is silly today. Nobody would dare imagine that somebody one day could imagine that. He imagines that generically it seems at least plausible that systems satisfying N15 form an open and dense set in the space of vector fields. This is, I think it's fantastic to see that such a great mathematician can be so naive. He imagined that most dynamical systems have a finite number of periodic orbits. Most orbits going non-periodic would be converged to one finite set of periodic orbits. Today, we know so many counterexamples. I'm sure that Poincaré would have immediately said it's wrong. Any counterexample comes to my mind. I mean, geodesics in negative curvature, et cetera, et cetera. And I think even Morse, probably when he saw that, should have said, no, forget it, it's not possible. But he published it. And Morse-Smale dynamical systems are interesting, but not so interesting. Well, Smale was not so bad after all. He uses ideas like Morse theory and many additional tools to prove his wonderful theorem in 1960, the Poincaré conjecture in dimension 5 and higher. Any manifold which has the homotopy of a sphere is homeomorphic to a sphere. And for that, the proof is Morse, 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 always. This is a fantastic tool, and he knew how to use it. So forget about my mentioning this bad idea about dynamical systems. So you see, any closed manifold which has the same homotopy type as a sphere is homeomorphic to a sphere. This is one of the great moments of the 60s in topology. I want to finish by mentioning this book by Milnor. It's a famous book. It's, well, I like this book because I read it many times. And it was my first encounter with Morse theory. I remember very well, I was an undergraduate student, and the professor mentioned the name of Morse during a lesson. And after the class, I went to the professor and I said, "What is it?" And he said, "You should go to the library immediately and take the book by Milnor." I went there, I remember very well. I came back home and I spent, I don't know how long, only reading this book. This is wonderful. And if you don't know how to write mathematics, go there and try to do as good as he does. This is just, for example, if you want to look the chapter on the Morse inequalities, I think it's not possible to write better. Okay, I'm finished. I just want to mention a photo which has been taken in 1963. You recognize the place. I like this photo very much because, you know, I think I read papers of all of them except two of them that I don't know. You know, look at that. This is just so difficult to find a better mixture of mathematicians. Both so I can tell you the only two that I don't know. Maybe somebody in the audience can tell me who they are. I don't know who is Poincare, and I don't know Thom. Somebody knew them? No? But the others are just top mathematicians. And it's amazing to see them on the same picture. Now, yesterday, I took the same picture at the same place so that I wanted to compare. Do you see a difference? There's only two differences. One, the door has changed. And two, the pavement is different. Otherwise, it's exactly the same. So for me, I hope you will forgive me, but when I arrived 2 days ago in front of this door, I had in mind this photo of my heroes. And then I said to myself, they are still there. So I believe that this institute is full of ghosts. Thank you very much.
Yeah, thank you very much, Étienne. So we have time for a few questions. Don't be shy. Everything clear? Oh, yeah.
The title of your talk is Slicing Space. So what you're actually slicing is slicing object in space. You're slicing objects in space. And therefore you're talking about surface perpendicular. How is really this related to I'm really going out to a tangent. Can we slice the space?
I'm not sure I understand your question. I just want to say that.
Well, I think if you talk that today, I'm going to talk about slicing objects in space. Yeah. I get you wrong.
You know, one of the things I mentioned when I mentioned.
Or a torus.
Yeah. When I mentioned the work of Möbius, he was slicing surfaces. But what is interesting is that he knew very well that he was describing surfaces up to homeomorphisms. But he knew very well that two surfaces which are homeomorphic might be not homeomorphic through a global homeomorphism of the space. So for example, a torus might be a standard torus or could be knotted torus. And Möbius knows that very well, and he makes that explicit. But when he slices the surfaces, he doesn't care about what's happening outside of the surface. He's just slicing surfaces. Did I answer your question?
I think what you perhaps mean is, so first of all, what is a space? So all the spaces we saw here, we viewed as lying in the three-dimensional space. So the slicing, I think what you mean is you have a function on that space and you look between two level sets. That's the slicing. And then what becomes interesting, if you go down and you reach a critical point, there are substantial changes in the nature of the space. And even infinite high-dimensional spaces with a function on it, you can always view as lying in a high-dimensional Euclidean space, a generalization of what we have, where the function is actually the last coordinate.
You have to know that the concept of abstract space is rather new. In the 19th century, nobody would speak of a surface independently of its embedding in three space. Even Riemann surfaces, these are awful pictures where they cross, but they don't cross. The abstraction of saying, I have a surface, I want to think it as a surface which is completely abstract, not embedded anywhere, is a very modern concept. I think I did not answer your question.
Yes.
What happens on a non-orientable surface like a Klein model or something?
That's the same question. Define people embedded in three space, and an embedded surface in three space is orientable. So what's happening is that Möbius does not mention that. It's clear for him that an embedded surface in three space has an interior and an exterior. So he doesn't mention this question of orientability. You're right, the Klein bottle is not embedded, and the Möbius band is embedded but has a boundary. So these kind of objects which are not orientable were not present in this discussion until very recently.
Any other question? Yes.
Who is working on this area today? What? Following that, have you published the corrections or the statements that weren't correct in these?
Oh, for example, if you take the mistakes or lack of precision of Möbius, for example, where now we have elementary books giving complete proofs. It was basically the same idea, but correct today. Maybe 100 years from now, somebody will say this is not correct, I don't know. But no, this has been fixed everywhere, yes.
Yeah, so you stopped with Witten essentially.
Yeah.
And there was after this was another revolution in 88, 86, 87, 88. And the class of problems where one could do this became much larger. And this kind of problems studied here can be understood as trying to study certain problems which are of interest in physics. So Euler in 1744 formally said it as follows: nothing in this, because of our wise creator, nothing in the universe happens without a rule of minimum or maximum being obeyed. So that was later a little bit generalized. What it means is, in modern terms, for basically all interesting problems in physics, you can build an infinite dimensional space you can put a version of calculus on that infinite dimensional space, perhaps then with infinitely many variables. There's a function on that space, perhaps a Morse function. And what happens in physics are precisely these points on that space characterized by being saddle points and so on. That is what you will see in classical physics. And if you're then in quantum mechanics, whatever can happen, happens, but with different probabilities. So that's so it's completely irrelevant. I mean, so I think originally it started trying to understand problems which come from physics, but you couldn't really do this, and it evolved further and further.
Sure. Minimum, maximum of all critical points more generally.
Yes. So for Euler, it was of minimum and maximum, and that's true in many, many cases. And this kind of...
If you allow me, you forgot Lagrange.
Yes, Lagrange, yeah. So there are actually quite a lot of people, before another French guy, Möbius, right? So who observed that, he said, what he said is, if light goes through a medium which is not homogeneous, then it tries to go in such a way that it comes fastest through this medium. So what it means, for example, if you are a lifeguard, you see somebody drowning, and this was explained by Feynman, then how would the lifeguard move? The lifeguard can move faster on sand, so he would run along the sand and then only goes into the water. And he observed, Möbius, that is with the light, and then he could explain laws of reflection and so on, Snell's laws and so on. So there's a fantastic transition, history in this kind of things, and still going on. And this variation of problems, for example, also explain how atoms are made out of quarks and so on. So it's just everywhere.
Montaigne went to the North Pole, or as close as possible to North Pole. He wanted to measure the Earth. So his problem was to find between 2 points in the Earth, the distance between 2 points. So you need to know the shortest path. And since the Earth is not perfect sphere, he has to understand how you determine the geodesic on a surface which is convex, but not spherical. And then he uses the minimization that you mentioned.
Yeah, so
okay. So the conclusion of Helmut is that we should look for the minimum.
Well, we look at, yeah, so, I mean, in general, it's just critical points, like minimum, maximum, saddle points, and so on. And there are really interesting stories around it. We can solve now and study more and more problems. And the interesting thing, Morse theory, you can explain as relating the number of critical points with a Morse index with the number of holes the space has. So there's another concept, that spaces can have holes.
If you want to know more about Morse theory, you look at the article by Bott on the left. They wrote this paper called Morse Theory Undomitable. This is just wonderful.
1988. Oh, yes.
Yep.
Yeah.
So the 60th birthday of René Thom.
Yeah. So there's actually a lot of literature about it. And in fact, in this 1988 paper, he gives actually the progression in the theory, Morse, René Thom, Smale, Witten,
yeah.
and Fleur, Andreas Fleur. By the way, I'm writing this. Yeah, so we have a commercial break here. So I'm writing a book about what Fleur did together with Siobhan Roberts, who is a journalist. She writes for the New York Times in the science section, and she's maybe even on Zoom here. And it will appear in 2026, and it will tell some of the story too. Yeah, so now since we inspired you now with more questions one can ask. Any more? Okay, so let's have our speaker again for this one of the slides.